We talked on Tuesday about probabilistic approaches to linear regression. Today, we're going to talk about linear classification, and we will again do it in a non-probabilistic way. You're going to again see models, you'll see loss functions, you'll see optimization formulations. And then next week, I'll walk you through the probabilistic version of this as well. So just to get started, I wanted to situate and motivate what it is that we're doing today. Again, here's our taxonomy. We're still in supervised learning. We're still training with training data and interested in making a prediction on a new example. And today we're talking about classification. So classification, think about trying to classify images as having dogs or cats. This is a discrete label that we're looking to make a prediction about. If we go to our cube, you can see that now, like I said, we're in the non-probabilistic area and we're doing discrete predictions. Classes are zeros or ones, they're discrete, not continuous. And we're still doing supervised learning. We're still imagining that somehow from somewhere we are getting labels to be able to train our model with. So it's hard to talk about classification without talking about the most famous example, or one of the most famous examples. And, you know, we don't tend to think about the USPS these days as being an especially innovative company. But back in the 1990s, it was indeed innovating. And it's considered a pioneer in the field of machine learning. And it's probably surprising to many of you. But if you think about it, the US Postal Service needed to be able to efficiently decide how to route envelopes that have been addressed often by hand and often with not very good handwriting. And they built a machine learning classifier to try to do that. Initially, you can kind of see here, if you're scanning this, it wasn't doing very well, but today it's doing extremely well. And the initial methods were neural network based. And the methods today are, I believe, still essentially neural network based, but not the same neural networks. Here's another example. One of the ways that we get training data for training classifiers is to get people to help. And in citizen science, you're trying to engage people online to help you to provide labels. In this case, labels of birds. So this is a beautiful paper from 2010, where they had images of ducks. What else do we see here? We see a red-necked grebe. We see Canadian geese, and this is also a duck that's kind of cleaning itself, I think. And what you can see if you look here is that there are two features. There's a feature in this dimension, which is kind of a feature that reflects how ducky is the bird. And there's a feature, actually this feature is how goosey is the bird. And this feature is how ducky is the bird. And you can see that the birds that are mallard ducks, for example, are in this part of the space. The birds that are Canadian geese with the little red triangles are in this part of the space. And the grebes are kind of in between the ducks and the geese in this part of the space. And then we've got a whole bunch of non-birds that are down here. They're neither goosey or ducky, right? And then the lines represent decision boundaries that are inferred for the way individuals responded. So you can ask kind of, how can I model the way a particular worker in the crowd seems to be discriminating? And the question they were asked was, tell me when you see a duck. So not tell me when you see a bird, tell me when you see a duck. And the researchers in the paper basically clustered the human responses into three types. There's the one type of decision boundary, which you can see is up here. These people are successfully separating the ducks away from the non-ducks. Okay, so these ones are doing well. There's a second cluster of decision boundaries here. These people are separating the ducks and the grebes away from the geese. And then there are other users down here that are roughly separating, look at kind of this cluster here. that are basically saying bird versus non-bird. So these users really don't understand what a duck is versus a bird, right? And it's kind of a nice example because you both see disagreements about where to draw decision boundaries. I've introduced this concept of a decision boundary that we will be working with today. And you also can begin to think about how you can use human data to make to label and then to train automated classifiers. Data match. I confess that I do not know very much about data match. I know there are people here who know quite a lot about data match. It is happening fairly soon, and it may or may not be using a classification algorithm. I don't know, but you could imagine this could be a classification problem. Last example, I was reading the newspaper this morning. This is an example of where to be careful with using classification technology. Facebook has said that it will no longer algorithmically recommend political groups to users. So this is a classification problem. It's trying to pick out the political groups that a user might be interested in. And there are concerns that the algorithm may have driven people to form social networks within groups that would not have otherwise been formed. Okay. So just a little bit there of kind of discussion and examples. I need to turn to my co-host here. Finale, what do you have to say about all of this?
I was going to say that I love the bird example, the duck example, and I think this is also a great example to think about the many layers that go into classification and implementing stuff out in the real world. So you pointed out, there's variation in people in terms of can they separate aquatic birds from types of aquatic birds from birds at all, from a scene with nothing in it. And there's those sorts of errors. But another piece that I think also comes out of OSU with these citizen science efforts is, okay, now you take this classifier and what are you trying to do with it? You're trying to maybe track migration patterns. You're trying to see what are the effects of building roads and other things through various wildlife areas. So are animals still able to get from one side of a region to another side of a region and stuff like this? And they found a very interesting result, which was that a lot of animals live near roads. This is not true. The reason why lots of animals.
I mean, so that doesn't seem right. So what was going wrong with the collection process?
Right. So what was going wrong is that people drive somewhere, they get out of their cars and they listen and they take pictures, and it takes people who are much more avid hikers and birders to go deeper into various woodland areas and take pictures there. So I think that's just a great example of just all the many layers of like how to think about what a system does and think about how it's going to be used out there in the real world.
Completely agree. And it also gets to incentive questions about how to motivate people to provide useful data. One other thing I'll just briefly mention is that about a decade ago, there were breakthroughs in regard to gesture recognition. Those of you that play games like Xbox-related games where you do stuff, and the game has to figure out what gesture are you using. The breakthrough didn't come from new machine learning algorithms. The breakthrough came from paying actors to provide gestures, and then essentially in a non-parametric way, trying to predict the gesture that you're showing by finding neighbors near you in the gesture space they'd collected from actors. So it's this kind of other cautionary tale that a lot of the power can sometimes come from the data itself. All right, thank you, Finale. And so what I want to do now is I want to jump into telling you now about linear classification. And let's set the scene by just kind of reminding us all that this is the picture I want you to have in mind. Imagine we have some positive examples and some negative examples. So this is my feature 1, feature 2, and this is a decision boundary. And maybe this is the direction in which kind of the score we're going to associate with these examples is increasing. And we're trying to find a decision boundary that correctly classifies, let's say, the examples in the direction of my arrow as the positive examples, and the examples away from my arrow as the negative examples. Our data will again be a set of labeled examples. Again, xn, think about as being in some d-dimensional space. Please don't confuse that d with my script d for data. And now think about an example, a label on an example, as being either +1 or -1. You can make this multi-class. For now, we'll just talk about binary classification. And so our goal is to predict y hat, a predicted class, on a new example. And we'd like to do that as accurately as possible. This is the classification problem. So I already hinted that one way you might do this is non-parametrically. So if you kind of reach back in your minds to a little bit over a week ago, we were talking about k nearest neighbor methods. And so what would the idea be for a k nearest neighbor non-parametric classifier? If you think about it for a second, there's really an obvious thing that you might do, which is to take a majority vote on the k nearest neighbors. Right? So it's probably the thing you would have all thought of doing. I won't belabor it, but you can also use kernel methods here. You remember that we introduced this big capital K, and you've been working with these things in your homework. There you would be taking essentially a weighted vote. Now these are good. They're flexible. And the way to think about a non-parametric method is you borrow more parameters as your data set gets larger and richer. Kind of informally how to think about it. The data kind of becomes the way to think about how to make a prediction on new examples. But the problem with non-parametric methods, as we discussed when we introduced them a little bit over a week ago, is they can be very slow on big data sets. You've got to kind of work with this 100 million set of examples and find the nearest neighbor. And you've got to do that at prediction time. There really isn't much of a training step when you're doing non-parametric things. It's all happening at the time you predict on a new example. Maybe one other thing I'll add is that they're not interpretable. We don't get to look at coefficients and kind of understand what the model is doing, because there are no coefficients. Okay. So it's fine. It's a straightforward approach. It can sometimes be useful. But what we're going to talk about today is we're going to talk about linear classification. And there's a new idea that we need to introduce, which is the idea of a discriminant function. We'll write this as h of w and x So just to be kind of completely consistent with what I'm going to do later, we're going to actually typically write x and then w. Doesn't really matter, of course. And this is a linear function. This is the crucial thing. So the linear function. So when we're doing linear regression, this was our model. This was the way we were predicting the target value. Now this is what we'll call our discriminant function. And the way that we'll make a prediction is we'll predict a y hat as +1 if the discriminant is positive and is -1 otherwise. You take your discriminant function, it's positive, it's a +1. If it's negative, it's a -1. So just to situate our thinking here, if I go back to kind of my earlier two-dimensional setting with my positive examples and my negative examples, and kind of think about drawing a line like this, this is our boundary. The discriminant function here is -x1 plus x2 plus 1. So and then the boundary, what is the boundary? The boundary is the line where the discriminant is 0. It's where you're really not sure if this is a duck or a goose. And the points lying on the line, you're really not sure. And then kind of in this direction, this is your positive increasing direction. You think it's, let's say our positive class is the ducks. So, okay, these are ducks. In the negative direction, these are geese. So I wrote down this discriminant function -x1 plus x2 plus 1. If you think about this, this is a bigger score for, sorry, that should be a 1, of course. This is a bigger score for smaller ones and a bigger score for larger 2s. So you can kind of see that the discriminant function is increasing up and left. This +1 controls the intercept down here. And then the other thing I just want to point out is that this vector I've drawn, this orthogonal vector to the boundary, that the direction of that vector is -1 plus 1, and that's given by the coefficients of the discriminant function. So we can already kind of learn a lot about how the mechanics of this are going to work just from this very simple example. Okay, so discriminant function is a linear function of the features, and greater than 0, we'll say it's a positive class. Smaller than 0, we'll say it's a negative class. Any questions before we continue? Okay. So let's just understand this decision boundary a little bit more. So generally, this is a hyperplane. If you think about 3 dimensions now, imagine a plane rather than a line if we're in 2 dimensions. And what is the hyperplane? The decision boundary is the set of points x such that the discriminant is 0. That's our decision boundary. In 2 dimensions, it's a line. And let's imagine kind of a picture like this, where, again, here's x1, here's x2. I've drawn my decision boundary, and I want to think about 2 points that are on that boundary. And I want to think about, in particular, a vector S that goes from one point to the other point. So let me just remind you, if you think about your vector calculus, that x plus s equal x prime. Yeah, so think about this as a vector x. Here's my vector s. That should be x prime, of course, equal x prime. And that gives me x prime. So that's my vector calculus. Now, what I want to do is I want to think about this quantity. This is the inner product between the coefficient vector w and vector s. And so we can go ahead and substitute for x prime minus x in place of s. So this is this guy. And now just by algebra, I'm just going to add w0 and subtract w0. Okay, I can do that, of course. And now because x prime and x live on the decision boundary, these expressions are exactly 0. And so I get 0. Now, this is equal to 0 because x prime is a point on the decision boundary. I remember that my weight vector here, my coefficient vector, does not ordinarily include w0. I'm holding w0 apart for most of today's lecture. Sometimes we do it either way. For now, we're holding w0 explicitly apart. And so what do we conclude from the inner product between w and s being 0? Well, hopefully you realize that you conclude that w is orthogonal to the boundary. And so we can think about it as w sets the orientation. So w is kind of choosing the slope, if you will, of the boundary, and it's doing that through defining the orthogonal vector. And one of the things that I'm just going to tell you, I'm not going to prove this, is think about D as the unsigned orthonormal distance between the boundary and the origin. It's the length of this line here. That's D. And you can show, I'm not going to prove this for you, but you can show that D is given by the absolute value of W0 divided by the L2 norm of the W vector, which is the square root of the inner product of W with itself. And this is an unsigned quantity. These are all positive numbers now within the fraction here. And so what do we conclude from this? We conclude from this that W0 sets the distance to the boundary. Excuse me, distance to the origin. So hopefully that builds some intuition. Got our W vector, think about it as the rotation, and think about W0 as being how far from the boundary we are. So if W0 is 0, we're going through the boundary. Any questions? This is like the geometry of how we're going to think about what it means to have a decision boundary here.
So will our
will our
decision boundary always be a straight line or not necessarily?
Will always be a hyperplane. In 2 dimensions, always a straight line. Why? Because we've written down a linear discriminant function, and it's the linearity of the discriminant function that is leading us to get a line or a hyperplane. Any other questions? Okay.
Yeah, I have a question.
Yeah, please.
So like if we have multiple things to classify, like you showed, can you hear me?
Yes, I can hear you, yes.
Okay. If we have just not just two, but like multiple things, like as you showed in the first example, will we change age to like multiple steps? Or will we like divide groups into two subgroups and like keep dividing?
Yeah, so for now, we'll just think about there being one discriminant function, not multiple discriminant functions. I'll say something slightly different towards the end of lecture. You're asking about the case where there are multiple classes, I think. And so for binary, one discriminant function, and you're saying for multiple, it is going to be multiple discriminants, and we'll get back to it at the end.
Okay, thank you.
And S is the set of X's that are classified that have discriminant equal to 0. So don't really worry about how you classify the ones right on the line. We actually typically will tie break to -1, but it's defined this way. That's how the set is defined. Okay, so we've got our discriminant function, we've got our decision boundary. And the question now we want to ask is, what is a loss function with which we can pick parameters that are good? And I want you to recall that y hat is given by this. That's our prediction using our discriminant function, which I'm writing out in full here. So what is a 0, 1 loss function? For a negative example, think about it like this. Think about plotting on the x-axis the discriminant value on that example, and plotting on the y-axis the loss on this example. Now, if it's a negative example, when the discriminant is positive, we're making a mistake. And so our 0, 1 loss function is 0 to the left of the axis here and 1 above the axis. We're making mistakes when the discriminant function is positive. That's when we're misclassifying our negative example. So this is a 0, 1 loss function. It's a step function. And I can also draw this for a positive example. And this will be flipped for the case of a positive example. So for a positive example, we're making a mistake when the discriminant is negative. I think that probably makes sense to you all. This is a 0, 1 loss function. We can write it down algebraically as being as being 1 if z is positive and 0 otherwise. That's mathematically what the step function is. So once I have my 0, 1 loss function, I can go ahead and I can write down, do you remember we have this notation for loss on my training data for a given parameterization W? So let's just go ahead and write that down. It's going to be the sum over all of the examples n. It's going to be the sum over all of the examples n of this expression. That expression takes a little bit to interpret. Let me explain this expression to you. So think about the case where y is a negative example. So when y is a negative example, when xy is a negative example, the picture I drew here, we want to pick up the loss in the case where z is positive. So what we do here is we negate the -1 to get a +1, and we multiply by the discriminant. And so this will return a 1 if and only if, on a negative example, the discriminant is positive. And similarly, now think about a positive example. For a positive example, this will be now, for positive example, yn is +1, so minus yn is negative, and now I have a positive number z that I'm feeding into my loss function, exactly in the case where the discriminant value is negative. And I see that what I've written here is not quite right. So I'm just going to not label that line with this L function, because notice I've defined my function L to take a z and return a 1 when the z is positive, and return a 0 when the is negative. So let's define L to be this step function. I want my loss on a positive example to look like this. I want my loss on a negative example to look like this. I think you will get that. And this is just the way algebraically that we make sure that happens, by just handling the signs in the right way so that we pick up positive quantities here when there's a problem, and therefore return a 1. And therefore you can write down a simple version of this as just the number of points that are misclassified. This all simplifies down just to counting how many points are misclassified. It's a 0, 1 loss function, and you can think about it as scaling with the number of mistakes. Okay. And let me tell you that the problem with this is that, think about, again, our simple example. Here are my pluses, here are my minuses. And we're going to want to be using gradient descent. I want to use gradient descent to follow the gradient vector in the direction of decreasing loss to try to minimize loss on our training data. Remind you, gradient descent looks like this, where eta here is my step size. And it decides how far I walk. It's a positive quantity. And I've got a negation because I want to be walking downhill, not uphill, because I'm minimizing loss. But now what's the problem? Suppose that this is my boundary. This is my current boundary. So my current boundary is classifying all of my points as pluses. But now ask, what is the gradient around where my parameters currently are? And it's 0. There is no gradient, because you can kind of imagine that for the negative examples, I'm like over here somewhere. My discriminant is way too positive, and there is no gradient around there. I don't get any information. Derivative is 0. I don't get any information. I don't know that if I kind of push this line a little bit this way, because you kind of imagine you want it to move that way, the loss wouldn't change. I'd still have the same 0, 1 loss. So I have no gradient to follow. So what we would say is we'd say the gradients of the 0, 1 loss function are uninformative. In particular, they're 0 almost everywhere. So this is not going to work for us if we want to be using gradient descent. Let me take some questions. Anybody have any clarification questions about what I just did? I think this thing probably looks a little bit mysterious, but I guarantee that when you stare at this will make sense.
So is that loss?
Could you clarify what's? Sorry, go ahead.
Sorry.
And let me propose you raise your yellow hand, and then I'll call on you all so we don't get you talking over each other. Skylar.
Yeah, so Professor, for the L of D of W that you wrote in that form, does that generalize for all of the data points or only for the data points where our target should be negative? I'm a little bit.
No, this is a perfect expression. Sorry, that's a bit Trumpian, but this is a mathematically correct expression for all examples by kind of very carefully writing down this minus y here. So if you stare at this, it will make sense, Skylar, I guarantee. You're basically making sure that this is positive if and only if there is a mistake on the example. If the example is negative, when is there a mistake? When the discriminant function is positive. So -1 minus times -1 is +1, this is positive. And you can check the same thing for a positive example. When is there a mistake? When the discriminant is negative. So on a positive example, we've got -1 multiplied by something negative, which again is a positive quantity. So it works for all of the examples. Let's go to Benjamin.
Yeah, could you just clarify what you meant when you said a positive and a negative example?
Yep, positive example is one for which y sub n is +1. Negative example is one for which y sub n is -1. And
so it's nothing to do with the step functions you drew.
Yes, so this is how we want the 0-1 loss to work as a function of the discriminant for a negative example. We wanted to return a 1 when the discriminant is positive. And this is how we want the 0-1 loss function to work for a positive example. We wanted to return a 1 when the discriminant is negative. And so we're going to manage to do that by writing down the single L01 function. And that's this function here, and feeding it this quantity. And this quantity will be positive if and only if there's a problem, irrespective of the example.
Okay,
and
thank you.
If you check it on some examples, it will all begin to make sense, I guarantee. And if it somehow is confusing as to how it's working for positive examples, just think about negative examples if you want, but it's working for both examples because of the sign flip here. Natalie?
I guess my question was, how do you choose what WT to start with for gradient descent, or how do you choose where to put the first boundary?
Yeah, so that's a great question. In the case where things work, it doesn't work here, but in the case where things work, you can start anywhere. Okay, so let me tell you how we're going to fix this problem with 0-1. So the fix to this problem is going to be the hinge loss. This is a beautiful idea. This is the highlight of today's lecture, so pay attention to this. Let me write down the hinge loss for a negative training example. So an example where yn is -1. This is the hinge loss. So it's z if z is positive and 0 otherwise. Okay. Remember that this is the region where we're making mistakes on a negative example. Let me draw the derivative of this. This is dw L hinge d dz, L hinge z. What's the derivative of that function? You will know that it's 0, and then it's a positive derivative at 1. So that's my derivative. Okay. Now, what's the interpretation of this? Let's go ahead and write down our loss function on our data. So as always, we take the sum over all of the examples, positive and negative, of now the hinge function, the hinge loss, again applied to the same kind of magic quantity that does the right thing for both positive and negative examples. This will give a z that's positive if there's a problem, irrespective of the sign of the example. And again, we can simplify this now that we have a hinge loss. It's 0 when we're doing the right thing. It's only positive when we're not doing the right thing. So I can sum out over all of the examples where we're making mistakes of the z, because it's just a linear function. So we were just taking ones. Now we take the z quantity, which is this quantity. And if you just kind of think about what this function is doing, this loss function is increases, it increases with more mistakes and worse mistakes. That's the crucial new thing that's been introduced by drawing this loss function. Now, as I move to the right, as I more and more discriminant incorrectly, my discriminant function gets more and more wrong for a negative example. I'm not saying loss is 1 all the time. I'm saying the loss is getting worse. And if you're following me, this means that gradient descent can now work. So the picture I want you to have in mind is this one. Again, here are my positives, here are my negatives, here's my current decision boundary. Now, if I move my decision boundary, if I follow a gradient, I'm going to somehow be able to move my boundary this way to reduce the errors that I'm making on these negative examples that are the wrong side of the decision boundary. So I have a gradient now. It's like I'm kind of over here and I want to move this way to the left in my one-dimensional picture up there. I think the last thing I want to tell you before we take a short break is that this is a convex loss function. And you know, what's the little picture for how you might think about what that loss function looks like? I think you can kind of think about it this way. And I'm just kind of going to imagine that our W is something I can draw in one dimension, just so I can kind of draw the picture. Think about it as over here, when I move to the right, I'm improving the error on 2 of my examples. At this point, I start doing the right thing on one of those 2. So now I'm improving the error only on 1 example. So my gradient is now less severe. And then at this point, I've got that example right. I'm now not improving the loss on any other examples. And then at some point, I start doing worse and then doing worse again. So I want you to kind of imagine, just like squint, and imagine that you're taking the sum over functions that look like this and functions that look like this. And you're taking the sum over those like individual loss functions that live on examples. And when you take the positive sum of convex functions, these are convex functions, you get a convex function. And because it's convex, gradient descent is going to work. You might be worried that the loss function is not differentiable. It's differentiable almost everywhere. It's just not differentiable right at 0. But because it's differentiable almost everywhere, that doesn't cause a problem. So technically, I don't want you to worry about this, but technically, if you're familiar with this, you're using a subgradient at that one point where there is no regular derivative. But it's not going to cause any practical problems. It's differentiable almost everywhere. It's convex, gradient descent with a fixed low enough step size will converge to a global optimum from any initial point. And this is something that we'll take as a fact about optimization with convex functions in this class. Any quick questions before we take a short break? Charu, please.
Yeah, so I was just wondering whether gradient descent would produce a decision boundary that was like very close to one of the classes or very close to one of the other classes, or if it would produce a decision boundary in the middle, since in all 3 of those cases, there's no loss.
Yeah, Charu, that's a wonderful question. And that is going to be the topic of much discussion in this course. For now, just kind of imagine that if the data is separable, we could end up at any separable decision boundary. And we're not telling it how to pick between them. And if the data is non-separable, there could still be multiple global minimum. And we're not telling it how to pick between them at the moment. But you're right to be potentially worried about that. Blake.
I'm just wondering if the 0-1 loss function in practice would ever be used in favor of hinge loss, or did you just introduce that to motivate the hinge loss?
Yeah, 0-1 is going to be pretty damn bad unless you're willing to solve a combinatorial optimization problem to train your model, which we typically don't want to do. If you're willing to use, if you've heard about integer programs, if you're willing to use integer programs, you could train a model with a 0-1 loss. Generally, we don't want to do that though, because it generally won't scale. Let's take 2 minutes. It just turned 11:19. We'll get back into. I'll start the breakout rooms just in case you want to hang out. And I'll share in case you want to stay more.
Might it be a little clearer if we don't label that bottom axis as z equals, because we're changing the notion of z across the positive and negative examples, just labeling it as w transpose x.
Yeah, maybe just labeling it z.
I was going to say don't label it z, just label it. Oh, this one's fine. Sorry, the one before, the one where we had the 0-1 loss, just for the version of the notes that we put up. Yeah, here I think we just want to label this as w transpose x plus w naught, because in one case the loss goes this way, the other one goes down. Yeah, exactly.
Oh, I think that's what I missed. That's just the prediction. Is the x-axis there?
Yes.
X-axis is the value of the discriminant function.
Oh,
Yeah,
that makes so much sense. Thank you.
Okay, yeah, this is.
There's so many negative signs and intermediate steps. It's definitely not the easiest concept.
Yeah, I think this is mathematically correct, this algebraic expression, and I think the pictures make sense too, the way they are now. Yeah, thanks.
Yep.
Okay. Great. So let's restart. And what I want to do now is I want to just make a few comments about where we are. One is convex functions can be, let's say, convex and differentiable. Functions can be minimized via gradient descent. Second comment I want to make is that this is not something I want you to understand why it's the case, but just it's a useful fact. Convex optimization is polynomial time solvable. And just as a comment, the 0-1 loss problem is NP hard, if you're familiar with that complexity class. And then, and this is just for a small enough step size. And we're not going to worry in this class about the theory for how small it needs to be, but you can, that is well understood. All right, so now what I want to talk about now is I want to be very clear about the difference between gradient descent and stochastic gradient descent. And you might be interested in really paying attention to this piece because it's less of a mathematical beauty than the Hinge function, but it's practically important, this distinction that I'm describing to you now. So when we do gradient descent, we repeat, update parameters W with step size eta multiplied by the gradient vector. And if you want to think about it, you somehow would think about taking the average over all of the data points n of the gradient vector on that point. I'm just going to kind of write like that. I just want you to think about that Hinge loss as being that more complicated expression with the minus y thing. This is gradient descent. The crucial thing is I'm working with all the data all the time. When I'm doing stochastic gradient descent, I am doing the following. I'm repeating pick random mini batch B. That's a subset of all of my data. Let me not write it like that. Subscript of all of my data, D. It's a subset of all of my data, D. And a node, perhaps mini batch size is 1. Mini batch is just a single example. And then what you do, you update W with step size eta times gradient on B. So now what you do is you do 1 over the size of B, the sum of the examples in B of the gradient vector on those examples. Same idea, you're just using a stochastically picked, randomly picked, maybe uniform at random, mini batch B. May just be a single example. And what are the trade-offs here? Well, gradient descent is more stable because you're calculating the gradient using all of the data. And in particular, just a fixed step size that is small enough will be okay for convergence. But a downside of gradient descent is it's very costly per step on a big data set because you're working with all of the examples. So then what is good about stochastic gradient descent? It's faster on large data. because you're working with smaller samples of data to find a gradient to follow. But its disadvantage is that the gradient becomes noisy because you're working with smaller samples to calculate the gradient. And in particular, to get stochastic gradient descent to provably converge, you need an adaptive learning rate. You need the step size or step size. Sometimes we call that eta as the learning rate. You need that to decrease over time. There's a more technical way to say it, but a typical choice is, for example, eta t, an iterate t of your algorithm is proportional to 1 over t. You're going to decay it over time. Intuition is that you kind of move enough so it's big initially, and then eventually you converge and you don't want to bounce around the optimal point. All right, so that's a little bit about gradient descent versus stochastic gradient descent. And just as an aside, let me just do the algebra with you for our hinge loss. And we can just go ahead and write the loss down for the points that are incorrectly classified, because those are the points where we have a gradient. Okay, and I've brought the minus outside. This is usually minus y. I've just written the minus there. And I want to note here that I have now absorbed the W0 into the weight vector. So now think about, you've introduced this column of ones into your feature representation. That's convenient when we use calculus to take the gradient. And so now, just using our rules of linear algebra calculus, I think hopefully now that you've worked your way through assignment 1, you can kind of look at this and know that the gradient will be this quantity. Right, so that's the gradient vector on all of my data. So that's an aside. And I just need to calculate it on the examples that are incorrectly classified. And then you can in particular write down stochastic gradient descent on hinge loss. And let's write it down in the special case where the batch size is 1. This is often just called SGD in the literature without any clarification. So what do? We pick an example at random. And if the example is correctly classified, so if y hat equal yn, do nothing. Else, we need to do our update. And this becomes a plus eta now because we have 2 negative signs. And we get this expression. And what I want to tell you is that there's a famous algorithm called the Perceptron algorithm. This is due to a researcher called Rosenblatt, who was a psychologist in 1958. Think about that. That's a long time ago. Rosenblatt, 1958, introduced what we would now call SGD batch size 1 hinge loss for the special case of step size equal 1. This is called the Perceptron algorithm. Famous algorithm, led to the AI winter in a sense because of Minsky's book, if you're familiar with the history of AI, just as a historical note. But there's an interesting theorem about this, and I just want to tell you the theorem. The theorem about the Perceptron algorithm is that perceptron converges if and only if the data is linearly separable. And I could give you some intuition on this, but I'm going to show you pictures instead. If and only if, so if data is linearly separable, Rosenblatt's algorithm will converge. If it's not linearly separable, it'll keep bouncing around. And this might appear mysterious to you, because didn't I just tell you that stochastic gradient descent converges as long as you're careful with your learning rate? And indeed, that's right. So the reason that the perceptron special case doesn't converge for data that is not linearly separable is because we're using a fixed step size. But just don't get tripped up on that. It's not a contradiction to the general success of SGD. It's just because Rosenblatt wasn't reducing his step size over time. And it ends up oscillating because of that. I want to make just a few quick comments, and I'm going to show you some pictures that I think will make this all make sense. And then we'll have a little time for a concept check. So just to go back to the question I got right at the start of class from Yintong, I think it was, which is that you can also think about multi-class classification, where now the target values are in one of k classes. We were doing binaries so far. And here's like a kind of a neat idea. Let me try to draw a light bulb. My light bulbs are often not that great, and that's a light bulb. Kind of the neat idea is that you can do what's called all versus one training, which is you simply train k separate binary classifiers. Take class 1, try to predict whether it's class 1 or something else. Class 2, is it class 2 or something else? And then you classify a new example as the class K with the optimal discriminants, with the largest discriminant value, where you have different parameters for each class. So I think that's probably intuitive to you as an idea. So you end up training K classifiers. They're each binaries. And then you squish them together at prediction time. Remark 2, basis functions. Okay, that's probably pretty self-explanatory. We've been doing linear classification. Remember that linear classification seems somewhat limiting until you realize that you can do basis transforms. I want to show you the Perceptron algorithm on a simple example from the Bishop textbook. Here, think about the red examples as positive, the blue examples as negative. Here's my current decision boundary. And here's my orthogonal W vector. Remember, the vector points in the direction of positive examples. And so in particular, first of all, kind of look at the data and see that there's a good decision boundary kind of here that would put the red points to the right and the blue points to the left. At the moment, we're making mistakes on these red points up here. They're on the wrong side of the decision boundary. And so what the Perceptron algorithm does is it picks a incorrectly classified example at random, say this green point, and it adds, remember I told you that the parameter update was the current parameters plus y of the example multiplied by the feature vector of that example. We had y sub n multiplied by xn. So as a positive example, I just add the feature vector corresponding to the misclassified positive example. So here's my current weight vector. I take the weight vector representing the error and I add it to my current weight vector. And the new weight vector will be this weight here. So take the current weight vector, add the weight from the misclassification, and this is my new weight vector. Here's my new decision boundary, because this is the orthogonal to the decision boundary. Repeat, pick another misclassified point. Oh wait, notice we're making progress. We've rotated the decision boundary here. Another misclassified point here, add that vector to the weight vector. Here's my new vector. Here, rotate it again. Now I'm successfully classifying. Okay, so it's just a look at Perceptron. Here's another look at Perceptron. This is taken from a web page that has a nice animation. On the left here, this data is separable. The green dots show you the point being picked at random. Eventually, on the left here, we will correctly classify. We're counting steps here. Okay, now we're correct. Now it's never going to move again. So Charu asked me kind of about this. So this is just where we happen to end up. You can end up in different points depending on the sequence. Ooh, it moved again because we just restarted. That's why it just moved. And then here, this just keeps iterating forever because it's not separable. And then you might think, well, okay, what about this basis function that I said? Here's data that is not linearly separable in 2 dimensions, but I can do a basis expansion, and then I can run my perceptron algorithm in 5-dimensional space, but still draw the decision boundary in 2-dimensional space, and eventually it will correctly classify this data. And then the last comment I want to make is that these methods will end up, there are multiple solutions, and right now we're not being clear about which one we prefer. And we might worry about that. So what I want to do now is, I want to go to the concept check. And here's my concept check exercise. Here are the 2 loss functions I've shown you so far. And here's another loss function, kind of a differentiable function and a convex function. And here's my loss expression. Maybe I said too much. So question 1, which loss functions are convex? Question 2, which training problem is NP hard? Question 3, which loss functions are differentiable? Question 4, which loss function cares about how bad an example is misclassified? Question 5, which function cares about how well an example is misclassified? I'm going to send you off into breakout rooms. We'll give you 3 minutes to chat about this, and then we'll come back together, and I will give you the answers. So I'll bring you back in 3 minutes. Oops. Let me try that again. Recreate all rooms. Okay. Hey, Mars. Not sure if I know how to push you to a room. Do you see the option? Okay, no worries. All right, welcome back. So here is the responses that we got. Question 1, which loss functions are convex? Yes, that's right. Hinge and logistic are both convex, 0, 1 is not. Question 2, which training problems are NP hard? That's right, 0, 1 is NP hard. Hinge and loss are convex problems, they're not NP hard. Question 3, which loss function are differentiable? A little bit of a split decision here. The answer is logistic. Hinge is differentiable almost everywhere. So you give yourself 0.8 out of 1 if you said Hinge is differentiable. Or if you want, you can give yourself like 1 minus epsilon out of 1, but it's not technically differentiable because of that point right at 0. Question 4, which loss functions care about how bad an example is misclassified? Good, both Hinge and logistic, because they both have that kind of increasing structure to the right of 0. Question 5, which loss function care about how well an example is misclassified? Good, only logistic. And I snuck logistic in. You haven't seen logistic before. It's something that we'll spend time talking about later in the semester. But you see how it has this slope here? So it also prefers to push things away from the boundary. So it wants things that are well classified to be even better classified. Just in wrapping up here, I want to just show you this. This is super awesome. So here's Rosenblatt. As I said, he was a psychologist at Cornell. And here, it wasn't just an algorithm, it was hardware. So here is the Mark I perceptron machine. Inputs being fed in via a camera system, a 2020 pixel map of a digit, a patchboard to reconfigure the inputs into the perceptron algorithm. And this is my favorite bit. This is an adaptive weight rack where each weight was implemented via a rotary variable resistor driven by an electric motor. And so what Rosenblatt had to do was he had to build a physical machine to do the gradient steps. And this is the same type of machine as the Mark I that was in the Science Center for the longest time, and now is moving to the SEC building. Hopefully, many of you will get to see the beautiful SEC building. Just before you break, want to just put out kind of a health check in a way for all of you and for the teaching staff, which is your PSET's due at 8 p.m. today. Please don't expect us to be able to be super ed responsive after, say, 3 or 4 p.m. this afternoon. Okay, it's kind of on you at that point. I will say that I have office hours today from, I think, 4 till 5:30. So you could come and hang out in my office hours if you like. And then tomorrow is a wellness personal day. So do try to take tomorrow, not worrying about your schoolwork and doing something else completely different. Okay, thanks all. I'm going to hang around for a while in case you have things you want to ask me about.
So just to check if we, sorry.
Yeah, Charu first.
Yeah, I was hoping you could just like go over the all versus